In this video, we're going to be finishing up chapter 16 and going through a process called the Chatelier's principle. And so the Chatelier's principle states that if you have a system at equilibrium and you apply a stress to it, you do something to change it, the system will respond by minimizing that stress. So like by going back to equilibrium. So essentially the system will attempt to regain equilibrium. So if we're at equilibrium and something happens and we're no longer at equilibrium, the system is going to move to get to equilibrium. So some things that we can do to stress a system is going to add a reactant to product, remove a reactant to product, change the volume or pressure of the system, and change the temperature. So let's talk about addition or removal of a substance. So considering this equilibrium here, and so this is going to take us through mathematically, and then I'll show you in class like kind of how you can think about it, not really mathematically. But at equilibrium, let's say we have these numbers. So my K value is 0.297. We have these numbers. Now let's say, what are we doing right here? So look at the differences in the numbers. What do? We added N2, right? So if I add N2, first of all, I'm no longer at equilibrium because my equilibrium constant is 0.297. If I look at where I'm at right now, now my Q is different than my K. So if my Q and my K are different, we're not at equilibrium. Remember, K was 0.297, so Q is less than K. If Q is less than K, I'm going to be shifting to the right because I don't have enough products, right? So we can think about it in terms of Q versus K. Adding something now changes the fraction so that we can figure out which way it's going to shift. However, we can also think about it as adding a reactant. Well, what are we going to do with more reactant? We're going to shift right. We're going to make more products. And that will then put the equilibrium, it'll go back to equilibrium. So addition or removal of a substance, and big note here, does not change the value of K. It will go back to 0.297 because we'll be removing some of the additional N2 we added when we move it to the right. So here's graphically kind of what's happening. We're at equilibrium and we're just kind of chugging along in equilibrium. Then we added a bunch of N2. Notice that when we added N2, okay, the amount of H2 starts to go down because when I shift right, I'm going to be using H2. And then the amount of NH3 starts to go up because as I shift right, the amount of NH3 goes up. And then you notice that the amount of N2 kind of goes down a little bit, again, because I'm going to be shifting it to the right to reestablish that. But if you look at the numbers when it levels out again, it's going to be the same value as before. So it might not be the same exact amounts as before, but it'll be the same ratio as before. So adding a reactant or removing a product will shift it to the right because of the same reasons, right? Your Q, in these cases, Q would be less than K. So if you were to actually sit down and calculate, like, what does the Q look like? What does the K look like? Q would be less than K. If you add a product or remove a reactant, now Q would be greater than K. So it would shift to the left. And in class, I'll give you a nice little table to kind of organize this information, but think about it. If I give you more products, you're going to make reactant. If I remove products, you got to make more products. If I remove reactant, we got to make more reactant. So you can also think about it in terms of the fraction Q versus K. So let's look at an example. If we have this equilibrium system, determine whether the equilibrium will shift to the right, shift to the left, or no shift at all. And then each of these 4 things. So go ahead and pause and see if you can get an answer. So for A, adding O2. If we add a reactant, we're going to shift to the right to make more products. Shift right to use the extra reactant We have too much reactant, so we're going to use extra reactant and we're going to make more products. And that will help us get back to equilibrium. K value does not change. They didn't ask us for this, but I'm just going to reiterate 1,000 times. K value is not changing. The actual amounts of reactants and products might change, but the ratio between them, the K value, is not going to change. All right, B, remove H2S. If I remove a reactant, now we don't have enough reactants, right? So we need to make more reactants. So we're going to shift left to make more reactants. And this in turn will be using a products. So the products will decrease a little bit because we're shifting to the left to make more reactants, but we lost reactants, so we need to go replenish it. Again, K value does not change. Remove H2O. H2O is a gas here. And so it is, so if we think about our K expression, which is equal to our Q expression, essentially, we have H2O, 2 over H2S, 2, and O2. We don't include the S because it's solid. Does not get included. That's going to come up in this last part. If you have something that's not in the equilibrium expression, it doesn't affect the equilibrium. So removing H2O, if I don't have a lot of products, we got to go make more product. So we're going to shift right to make more products. This will uses reactants. So we will see a decrease in the amount of reactants, but we're making more products because we lost products. K value does not change. There is a situation where the K value changes. I'm just reiterating there and when it doesn't change. D, add S. This is a solid, so no change. Because liquid and solid have no effects on equilibrium because they aren't in the equilibrium expression. So they're not actually going to be changing the Q or the K numbers. All right. So what happens if I change volume or pressure? So when we're looking at a system that has gases in it, we can compress gases, right? We can change the volume and change the pressure. So if we have an equilibrium mixture, and let's say this is our K value, if we decrease the volume by half, the concentrations would then be doubled, right? Because we decrease the bottom number of that molarity. And if we plug these new numbers in, we get, hey, we're not at equilibrium anymore. Now our K, so if our K is 4.65 times 10 to the negative 3, Q is 9.31 times 10 to the negative 3. Now we have a Q greater than K, and we know Q greater than K means a shift to the left. So it'll shift to the left to calm that down a little bit, to lower that ratio. And then we'll go back to the normal K value. So we'll not change the value of K. We're actually just going to go back to the normal K value once that shift is over. We can think about it as if you decrease the volume, decreasing volume is increasing pressure. So it will shift to lower pressure. To lower pressure, we need less, we need fewer, let me use the correct grammar, fewer moles of gas. So if we look at the chemical reaction, we have 1 mole of gas on the left side and 2 moles of gas on the right side. So if I increase the pressure, we want to move towards fewer moles of gas to then decrease that pressure back to normal. So it'll shift left. You can also think about it in terms of Q or K if you're told, you think about the concentration and the volume changes. So why don't you try these three? If the volume decreases, so if the volume gets smaller, what would happen? Would it shift right or shift left? So for A, if you are decreasing the volume, so remember decreasing volume is the same as increasing pressure. So if we increase pressure, we want to shift towards fewer moles of gas. So if we look at A, we have 1 mole of gas on the left side, and we have 2 moles of gas on the right side. So we're going to shift left. You can also think about it as if you decrease the volume, that's like doubling the concentration. And I didn't give you concentrations, and so you can't really do the Q expression there. But you can think about it in terms of the just go to fewer moles of gas. All right, so for B, we have on the left side 3 moles of gas. Don't count solids and liquids. And you don't even count aqueous, you're only counting gas here when we're talking about pressure and volume versus 2 moles of gas. So this would be a shift to the right because we're trying to lower the pressure again. So I said shift right and wrote shift left, shift right towards the smaller moles of gas. So we're going to shift towards fewer moles of gas. And then C, we have 2 moles of gas on the left side, and we have 2 moles of gas on the right side. So no shift because it won't change anything. All right, and the last little piece is changes in temperature. So I want you to treat heat as a reactant or a product. That's going to help you think about it in terms of like adding something or removing something. And then here's a big change. Actually they have it. Change in temperature alters the value of the equilibrium constant because we're shifting things without actually adding or removing any substances or any amounts of substances. So the shift will change the value of K. So let's look at this example. This is an endothermic process. I know that because the delta H is positive. And I know over here we're starting with, it gets darker, right? Where it gets darker in color. So we're starting with less N2O4 or less NO2. NO2 is reddish brown and N2O4 is colorless. So right now we're starting with less NO2. And we heat it up. We can see we're heating it with the Bunsen burner here. We heat it up, it gets more reddish brown, which means it shifted to the right. We see visually it shifted towards more NO2. How do I know that? Because NO2 is more reddish brown and it got darker reddish brown. So if it shifted to the right when we added heat, we got to think, where was the heat? If the heat is on the right side and we add heat, it would shift left. So we would see it get more colorless. If the heat is on the left side and we see a shift right and it got more brown, then that's what matches, right? So heat is on the left side because it's endothermic. And so if we add heat, it's going to shift to the right. So here's a slide that talks to you about where heat is. If it's endothermic, heat is a reactant. And so we can think about adding heat would shift it to the right, removing heat would shift it to the left. If we shift it to the right because of heat, K would increase because we're increasing the amount of products, decreasing the amount of reactants, but we did not increase or decrease the amount of reactants before that. So K is just going to go up. If you shift the toward the reactants, shift left, K would go down. And that's just true of if you change heat, that's how it'll affect K. Exothermic reaction, heat is a product. So adding heat would shift it to the left, K would go down. Removing heat would shift it to the right, K would go up. That's all for chapter 16. We're going to do more of this in class.